Suppose you're part of a crew planning to rob a bank. You know how quickly your getaway car can travel and where the bank is. You also know where the nearest police station is and how quickly a trained officer can drive. It's your job to figure out how long it'll take the cops to catch up with you and your crew. This problem is one example of the many uses of a system of linear equations. The travel of the cops and robbers can each be represented by a single linear equation that looks like this, or this. Any situation where two or more of these equations are used at the same time will create a system of linear equations as described in Common Core Standards 8.EE.8.a. Now, it can be intimidating to solve something that looks as complex as this, but I'm going to take you through a couple of different solution methods that can be used to quickly and easily arrive at the correct answer. The first method of solving a system of linear equations we're going to talk about today is graphing. What we can do is we can plot each equation onto a blank set of axes that looks like this, look for their intersection point, and that will give us our answer. Now, our first equation that we want to work with is going to be y equals 2x minus 2. Looks like this. It's already in slope-intercept form for us, which makes things easy because we can easily see that our slope is 2 and our y-intercept is negative 2. If we take that and plot it on our points, we'll get a line that looks like this one. Next thing we want to do is graph our second equation, which is going to be 3y equals x plus 9. This is not already in slope-intercept form, so we want to go ahead and divide both sides by 3 to get it that way. And that will allow us to cancel that out, get y by itself. We're left with the equation y is equal to 1/3 x plus 3. Now with that, we can easily see our slope is 1/3, our y-intercept is 3. Using that information, we can then plot that equation as well. We get the second line on our set of axes that looks like that. Now those two lines cross each other at a single place. If we follow that intersection point down, we can find our x value is equal to 3. If we follow that intersection point to the side, we can see that our y value is equal to 4. Thus giving us the answer, or the solution, for the system of linear equations of x equals to 3, y equals 4. If graphing sounds like too much work, the system can also be solved by substitution, where you take one equation and plug it into another one, solving for one of the variables. You'll notice that our first equation is already solved for y. We get y is equal to 2x minus 2. What we can do is we can take that 2x minus 2, plug it into our second equation for the y value, and end up with the combined equation of 3 times 2x minus 2 is equal to x plus 9. Now from there, it becomes relatively straightforward to solve for the single variable we have left over. We distribute the 3 across, and we end up with 6x minus 6 is equal to x plus 9. From there, add the 6 to bring it over, subtract the x to bring it over. You have 5x is equal to 15, or x equals 3, just like before. Now the last step to do is to take that x equals 3, plug it back into our first equation, y equals 2x minus 2, and we'll be left with y is equal to 2 times 3 minus 2, or 6 minus 2, or 4. And there we have, once again, x equals 3, y equals 4. One last thing to be aware of is the fact that systems of linear equations may not just have one solution. There are cases where the two lines will run parallel to each other that will yield no possible solutions, and other cases with the lines right on top of each other producing an infinite number of solutions. The important thing is to always take your problem solving one step at a time and be aware that the answer might surprise you.